Hi to all. Today's topic is continuation of potentiometer class 12 current electricity. Then the topic is that determination of internal resistance of a cell by using potentiometer. Right? What is potentiometer? What is its principle? And how we can compare the EMFs of two cells by using potentiometer, that already we discussed. Now I am going to continue one more use of potentiometer is we can determine the internal resistance of a cell by using potentiometer. This is the circuit diagram to determine the internal resistance of cell. Okay, look at here. This is already potentiometer up to here, the lower part. This is the potentiometer and this is the cell and internal resistance. This is the driving circuit. This is the driving circuit. In the driving circuit, this is the driving circuit, right? This is the driving circuit. Now in the driving circuit we have the one cell, okay, rheostat, internal resistance of the cell, and these are the 1 meter length manganese wires. They are connected by using the copper strips. And now the cell whose internal resistance is to be determined. For which cell you want to determine the internal resistance? Okay, this cell, okay, whose EMF is E and internal resistance is small r, that I want to determine the small r. Then here the small r is equal to what? This is question mark. And then I want to determine the small r. Then for that, which cell EMF you want to determine, that cell you have to connect to point A. Okay, and then we have to connect one external resistance capital R in parallel to the cell whose internal resistance is to be determined. Now let us see what is the procedure and how we can determine the internal resistance of cell by using this potentiometer. It was very simple. Okay, now a cell whose internal resistance is to be measured connected to point A as shown in figure. This is the cell, its internal resistance I want to determine, and that I have to connect to the point A. Okay, across that cell I have to connect a resistance capital R in parallel. Now first what we have to do, the plug key K is closed and K1 is open. Where the K is there, here the K plug key we have to close, then the current flows through the potentiometer wire. Okay, the current will flows like this, that current is I. And now here after that we are opening the K1. K is closed and K1 is open. What is K1? This K1 is open. When K1 is open, the resistance will not work. Right? This branch will not work. And only the cell will active. Cell E is active. Right? At that moment what you have to do, press the jockey at various points on the potentiometer wire. At a particular point N1, the galvanometer shows the zero deflection. Then at that moment you note the distance of the balancing point from point A, right? This is 100 centimeters plus this one, and when we will add this total, then we will get the balancing length. That balancing length is AN1, A2N1, that is we can note it as L1. Now according to potentiometer principle, what we know? According to potentiometer principle, what is the potentiometer principle? Potential difference across the wire is directly proportional to its length. That means now V proportional to L, and from that we will get one equation, that is V is equal to phi L, and where the phi is the potential gradient, right? Potential gradient, that we know already. Now let us see what is the V in this case. Okay, let us see what is V in this case. The V is that in this case V is the potential difference. Okay, for example this we will take as V1 and this we will take as L1. Okay, what is the V1? V1 is the potential difference between A and N1, that is the balancing length is L1, and V is the potential difference between the A and N1. Okay, according to potentiometer principle, potential difference is equal to potential gradient into balancing length. Potential difference across A and N1, potential difference across the wire equal to potential difference across the cell. This K1 is open, this will not work. Okay, potential difference across A and N1 is equal to potential difference across the cell. Then only galvanometer shows zero deflection. Now potential difference across the cell we know already, that is V1 formula is only one cell is there, V1 equal to E minus IR we write. But at balancing condition I is 0, then when we write I is 0, then V1 is equal, we will get as only EMF of cell. Right, here you substitute V1 as E, then we will get as E is equal to phi L1. This is equation 1. Okay, it was very simple. Next what we have to do now, close the plug key K1 and note balancing length. Note balancing length. Again we have to, firstly the K1 is open. Look at here, K is closed and K1 is open. Okay, then we are noting the balancing length. When K1 is open, only what will works? Okay, only cell will work, cell is active. At that moment we are noting the balancing length as L1. Next what we are doing, here the K1 is closed. The K1 is closed. When the K1 is closed, right, at that moment this resistance will inactive in position. Right, at that moment the balancing length you have to note as L2. Right, L2. From where to where? Okay, how to note the balancing length? After closing the plug key K1, again press the jockey at various points on the potentiometer wire. At a particular point N2, if the balancing length, if the galvanometer shows the zero deflection, then note the distance of point N2 from A, that will become the balancing length. Okay, right, that is AN2. AN2 is equal to, we will get as L2. Okay, now again according to potentiometer principle, what you will get? According to potentiometer principle, according to potentiometer principle, right, we know already potentiometer principle, V2 is equal, we write as phi L2. We know potentiometer principle, that is Vi is equal to phi L. But the thing is that here the second time balancing length L2, L is L2 and potential is can consider as V2. But what about the potential V2, whether it is 0 or not? Okay, now the potential difference between the A and N2, this potential difference across the potentiometer wire is equal to potential difference across the cell. But what about the cell? Here we are noting the balancing length when the galvanometer shows the zero deflection. Then here when the galvanometer shows the zero deflection, whether the current through the cell is 0 or not. Here the current through the cell, when the plug key K1 is closed, okay, when the current through the galvanometer is 0, even though some current flows through the cell. How? Previously there is no current. Here we are telling that when in the previous case, when the plug key K is closed and K1 is open, K is closed, this is closed and K1 is open, this is not there. Okay, only one line like this there, right? And here we got the galvanometer zero deflection at this point. That means here the current 0 means along this line there is no current, right? This branch is not there previous case, but now we are closing the K1, at that moment this branch is also there, right? Now here the galvanometer shows the zero deflection, at that moment we are noting the balancing length as L2, but here the thing is that here the current through the galvanometer is 0, even though some current passes in this circuit. Current will not come outside because galvanometer showing the zero deflection, at that point only we will note the balancing length. That's why galvanometer will not show zero deflection even though some current passes in this circuit. Then how much current passes, right? And then at that moment the current will not equal to 0. The current is not equal to 0 because here there is another path is there to flow the current, like this the current will flows only in this circuit. The current never come outside. Galvanometer zero deflection shows the zero deflection even though some current passes through the cell. At that moment the potential difference across this potentiometer wire equal to potential difference across the cell, but that is not equal to EMF because it is not, current is not equal to 0. Potential difference across the cell formula is V2 is equal to E minus IR. When I is not equal to 0, then V is also not equal to 0, right? V is not equal to E, right? I is not equal to 0, there is no current, current will not become 0, current will not become 0 means then V2 is not equal to E. Here we write the V2 is equal to V, we can write. Let us consider V2 is equal to V, not equal to E, that we can consider as V. then we will get as V is equal to phi L2. This is equation 2. This is the important point. And now let us divide the two equations, equation 1 by equation 2. What you will get? That is E by V is equal to phi L1 by phi L2. That is E by V is equal, we will get as L1 by L2. Okay. Now let us see, but we know what is the formula for V. V is the potential difference across the cell. But potential difference across the cell equal to potential difference across the resistance. We write V is equal to IR. And how we write the EMF of cell in this circuit? If you want to write the EMF in this closed path, current formula if you want to write, the current is equal to, here effective EMF E by effective resistance is small r plus capital R, or the capital R in this closed circuit. Capital R plus small r we write effective EMF by effective resistance. Effective EMF is E, effective resistance is capital R plus small r. Right? Here from that E formula we can write E formula. You can take this to left side, then we will get as I into capital R plus small r. These two equations we substitute in above equation, then we will get E as I into capital R plus small r by V is equal to IR. You substitute in this L1 by L2 we will get. This I gets cancelled and we can simplify this equation, and this we write as capital R by capital R plus small r by capital R. Okay, capital R plus small r by capital R. Capital R by capital R plus small r by capital R is equal to, we write as L1 by L2. This is capital R by capital R is 1 plus small r by capital R is equal to, we write as L1 by L2. Then finally what you will get the equation. Okay, let us see what you will get the final equation. We can continue here. The final small r by capital R is equal to what you will get. Okay, the small r by capital R we will get as L1 by L2 minus 1, right? Okay, this plus 1 goes to right side. Then I want the small r. Small r is equal to, finally we will get as L1 by L2 minus 1 into capital R. This is the final formula to find out the internal resistance of a cell. This is equation 4. This is equation 4. Okay, and this is the formula and derivation, and by using that formula we can find out the internal resistance of a cell. Let us see here. While finding the internal resistance, what we required, L1 is required, L2 is required, capital R is required. Capital R is already you know, right? What is L1 and what is L2? Okay, right. L1 is the balancing length with only cell, right? Because here L1 we are noting the balancing length when the K1 is open. K1 is open means this is not there. L1 is the balancing length with only cell E. L2 is the balancing length with the cell and a parallel resistance capital R. Okay, K1 is closed. I will tell what is the procedure in 1 minute. First we have to K1 close the K and K1 is open. Press the jockey at various points and note the balancing length, that is L1. Next, K1 is closed. Press the jockey at various points on the potentiometer wire. At a particular point, the galvanometer shows the zero deflection. Again note the balancing length, right? That is L2. After noting the L1 and L2, you substitute the values of L1 and L2 in this equation, you will get the internal resistance. This is the simple method to determine the internal resistance of a cell. And now you note every point and take the screenshot and write the notes, and then I will rub and I will continue the topic. Okay. Okay, let us see what is L1 in this equation. Finally, we got equation 4 as small r is equal to what? L1 by small r is equal to, we got as L1 by L2 minus 1 into capital R. L1 is the balancing length with only cell in secondary circuit. Okay, L2 is the balancing length with cell and a parallel resistance. Balancing length when a resistor, due to water it is not showing letters, when a resistance resistor of resistance capital R, when a resistor of resistance capital R connected parallel to cell, right? Parallel to cell. When we connect a cell parallel to the, when we connect a resistance capital R parallel to the cell, at that moment balancing length is L2. L1 is with only cell, L2 is the cell and resistor, right? Okay. Now let us go for the next topic, that is what is the sensitivity of potentiometer. Let us go for sensitivity of potentiometer. It is a previous question, how you will increase the sensitivity of potentiometer. What is sensitivity? If any potentiometer measures the small potential difference, then it is more sensitive, right? And now if a potentiometer is more sensitive if it measures small potential difference. Okay, on what factors the sensitivity depends? The sensitivity of potentiometer inversely proportional to potential gradient. How you will increase the sensitivity of potentiometer? Okay, very important point this one. By decreasing potential gradient, we can increase sensitivity. Okay, right, look at here. Sensitivity proportional to potential gradient. But what is the potential gradient? Potential gradient is the potential difference by length. We know already potential gradient formula, that is V by L, potential drop by length, that is IR by L, right? And this we will get as potential gradient, we can write here. Potential gradient is the phi. Okay, phi we can write here. This phi is nothing but IR by L. L goes to numerator, then we will get like this. Okay, if L and R, if L length of potentiometer wire increased, if L is increases, then sensitivity increases. If length of potentiometer wire increases, or if resistance of potentiometer wire decreases, if resistance decreases, resistance of potentiometer wire decreases, then sensitivity increases. Okay, R decreases means sensitivity increases, L increases means sensitivity increases, because sensitivity and L proportional, right? Then sensitivity increases. Sensitivity increases. Okay, and now this is what is sensitivity. Sensitivity is it refers the smallest potential difference measured by the potentiometer. If small potential difference measured, then its sensitivity is more. Sensitivity depends upon the potential gradient. That is how you can increase the sensitivity. Then by decreasing the potential gradient, we can increase the sensitivity. Now let us see. Sometimes we will get the one side deflection in the galvanometer. Okay, and what are the precautions we have to do? Why the galvanometer shows one side deflection? What is one side deflection? Actually, when you will connect the potentiometer, right, after completion of connections at the both ends of potentiometer wire, you have to press the jockey. Then the galvanometer shows the opposite deflections. Then at that moment in the middle here, for example, we have the circuit. This is the cell whose EMF is E, and now this is A. Internal resistances are not, and this is the series resistance RS. This is the point A. Here we are connecting to some battery whose EMF we wanted, whose internal resistance we want to determine, and this is one external resistance. Here we are connecting to galvanometer. The galvanometer is connected to jockey. Okay, this is jockey. First jockey you can press at this point. Galvanometer shows one side deflection. Galvanometer at the middle 0 it is there. This side readings will be there 20, and this side readings will be there 20. And when we will press the jockey at a point A, the galvanometer should deflect in one side. When we press the jockey at point B, the galvanometer pointer should show deflection in the opposite direction, right? But if it will not shows the opposite direction at point A and at point B, it will shows the same direction. And when it will shows the same direction due to some wrong connections. Okay, for example, here it is showing the right side, here it is showing the left side. When somewhere at the middle it will shows the 0, right? And that means galvanometer shows the 0 deflection. Now let us see. I will write by pressing the pause. Okay, let us discuss two important points. What is the cause of one side deflection in the galvanometer? That means when you will press the jockey at here and at here, galvanometer shows only one side deflection. The reason is that the connections may be wrong. As per circuit, the positive terminal of this cell and the positive terminal of this cell should be connected to the point A. But if they are not connected, for example, negative connected to A, or the negative of this, something wrong like this. If negative of this is connected to point A, then it will be wrong. The positive terminal of this cell and this cell, positive terminals of all cells should be connected to point A, but if they are not connected, then it is a mistake. Due to that, you may get the galvanometer one side deflection. And the next one more point is that the condition is that to get the accurate experiment values, EMF of this driving cell, this is said to be driving circuit, EMF of driving cell should be greater than the EMF of the cell in the secondary circuit. But due to any reason, if the EMF of this cell is less than this, then it will not show proper result and it will give the one side deflection. That is, the EMF of driving cell is less than the EMF of cell in the secondary circuit. That means E0 less than E1 or E0 less than E2 or E0 less than E, right? Due to that, if the EMF of driving cell is less than the EMF of the cell in the secondary circuit, this set to be secondary circuit, at that moment you will get the one side deflection. Okay, these are the two causes why the one side deflection is occurred. One is all the positive terminals should be connected to point A, but if due to mistake if any one negative terminal is connected to the point A, then that is the one mistake. Next, one more mistake is that the EMF of this cell should be more than this, but if it is less, then again one side deflection will shows, right? Good. And why potentiometer is better than the voltmeter? Potentiometer is used to measure the potential difference, voltmeter also used to measure the potential difference, but potentiometer measures the EMF or potential difference without drawing any current. That's why potentiometer is better than voltmeter. Why? Because at the balancing condition potentiometer does not draw any current, but we are measuring the EMF at the balancing condition. That's why potentiometer is better than voltmeter. Now let us see one problem based on this and let us close today's topic. Okay, let us go for the one problem, and this is the last problem. And look at here, given figure shows a 2 volt potentiometer. This is a potentiometer with a 2 volt battery. Okay, and this is the driving circuit. Okay, driving circuit. Here this is the EMF of driving cell 2 volts and it's a series resistance RS. Through plug key we are connecting. Between the A and B 10 separate 1 meter wires will be there. They are connected in the parallel. Like this we are connecting. Okay. And now here this potentiometer is used to determine the internal resistance of a cell whose EMF is 1.5 volts. That we are connecting it here. Okay. Its internal resistance I want to determine. R is equal to question mark. Okay. And then first what they did means, first the balancing point of the cell in the open circuit is 76.3, means only when we will use only cell with the cell, okay, whose EMF is 1.5 volts, balancing length we got is what? 76.3 centimeters. 76.3 centimeters. Now with the cell, next what we are doing, when a resistor of resistance 9.5 ohm is used in the external circuit, in this external circuit we are connecting the 9.5 ohm parallel, again noting the balancing length, that we got is balancing point is shifted to 64.8. That means with only cell the balancing length they give, with cell and external resistance. Okay, external resistance, balancing length they gave us 64.8 centimeters, and the capital R also they gave how much external resistance we are connecting, 9.5 ohm. They are asking to find the internal resistance of the cell, this cell internal resistance. It was very simple. We already discussed how to determine the internal resistance of cell. With only cell the balancing length is L1. With only cell the balancing length is L1. With the cell and resistance the balancing length is L2. Then what is the formula to find out the smaller? That formula we derived, L1 by L2 minus 1 into capital R. L1 is the balancing length with only cell, L2 is the balancing length with cell and a parallel resistance. It was very simple. Now we substitute. L1 is 76.3 by 64.8 minus 1 into capital R is 9.5. Right? Now we can simplify this. 76.3 minus 64.8 by 64.8 into capital R is 9.5. Now 76.3 minus this, we can simplify this and easily we will get answer, right? Okay, look at here and you can simplify yourself. 76.3 minus 64.8 by 64.8 into 9.5. You will get 1.7 ohms. Okay, check it whether you will get or not. And now with this, today's topic is completed and this is very important. And I gave one question at here. It is also similar to this one. Okay, with the only cell balancing length they give, with the cell and resistance balancing length they give, we have to find out the internal resistance of the cell. The same formula you can use and give the answer in the comment. Thank you for watching my lectures. Subscribe and share to your friends. Thank you.